Okay, welcome to this video for Material Science 410, where we'll be discussing some of the fundamental chemistry and materials properties of silicone elastomers. So silicone elastomers are known to be a broad class of synthetic compounds, and they're composed of main chains. So if we were to cartoon a polymer chain as a long noodle, and we were to zoom in on a small portion, we would see here that this small portion is comprised of alternating silicon and oxygen units down that main chain. Okay, so dot, 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 dot. Since we know silicon is below carbon in the periodic table, we also know that the bonding must be satisfied just like carbon. So we would expect that there should be side chains coming off the carbon to provide fourfold covalent bonding at every carbon site. Okay. And so typically the functionality at these side chains can tune the properties of the silicone polymer. Some of the properties include chemical and heat resistance. The materials tend to be very rubber-like. They're easily molded into custom shapes. And they're known to be very highly resistant to tearing due to some of the strong bonding in the main chain. Applications that exploit these properties include a wide range of industrial and consumer uses, some of which are listed here, such as automotive parts, cookware, bakeware, sportswear, footwear, and home repair. And likely you're familiar with things like the home repair, like silicone caulking for your bathtub or around your kitchen sink, silicone cookware or spatulas to help kind of remove food from cookware or dishes. And the low surface tension of silicones is advantageous for the cleanup. And of course, the thermal and chemical resistance comes in handy with the automotive parts, for example. So as we mentioned a moment ago, silicone polymers are an inorganic organic polymer due to the presence of the silicon and oxygen features and in the main chain, and those side chains here shown as a generic R group must be present as well. And some of the more common options there are methyl CH3, ethyl CH2CH3, even phenyl, which would be C5H6 as a appended benzene ring. Or later in the lab, we'll see a vinylic group, so bonded to a carbon bearing a double bond and a hydrogen. So this functional group, called the vinyl group, it will be key to a hydroxylation reaction for cross-linking and setting the shape of the silicone polymers in this lab. So to generalize, silicone polymers are known to have a chemical repeat unit listed as R2SiO, where now we include the two R groups in the repeat units. So that square bracket in our bullet down here would represent everything in here, and thus the repeating pattern of R2SiO. And again, R here is generic and can be further specified both in formula and in name, depending on the silicone in question. Polydimethylsiloxane, in fact, is one of the more kind of common silicones known. And of course, the formula suggests that we have the siloxane, so that's the SiO repeat unit in the main chain, so the polysiloxane. And the dimethyl part of this name indicates that those side groups are methyl and methyl. So PDMS would have the formula square bracket CH3 twice SiO and repeated N times. Polydimethylsiloxane is a colorless and transparent elastomer, and this can be exploited for having clear caulking or in the fabrication of microfluidic devices that allow for the tracking of chemicals and other entities throughout the nanoscale channels that can be fabricated into that material. So here's an expanded formula of polydimethylsiloxane, where R here would of course be equivalent to CH3 for the PDMS. Or later, as we'll see in the lab, we'll have an option where that R group can be substituted with the hydrogen to make polyhydroxysiloxanes. And that SiH bond is reactive towards an Si vinyl group, as we'll see. Okay, so these two groups will react to help set our silicones, as we'll discuss in this lab. Other properties of the materials at the molecular level are reflected here. So the silicon-oxygen bond is known to be about 1/10 of an angstrom longer than your typical carbon-carbon single bond. The polymer ends up taking advantage of that extra distance and allows for more easy rotation about these single bonds and the extra space between methyl side chains along the repeating unit. And this allows the material to have more flexibility and provides the properties like the elasticity and the rubber-like properties that we see in many silicones. The SiO bond is also known to be stronger than the carbon-carbon single bond, about 150 kilojoules stronger than that carbon-carbon single bond. And that is to say that the silicon-oxygen bond has a strength of about 450 kilojoules for every mole of those bonds. And this allows silicones to be chemically resistant, more so than carbon-based polymers typically. In addition, since we have oxygen, which only needs 2 covalent bonds to satisfy its octet for bonding, we have no side chains at the oxygen, and this allows for more free volume between methyl side chains or other side chains down the silicone polymer backbone. This extra space and the lack of side chains allows for more easy free rotation again. This, in addition to the extra length, as mentioned above, allows for a very low glass transition temperature, which is the temperature at which a polymer transitions from being hard, brittle, or glassy into something that is viscous and more rubbery. And so this temperature for this glass transition temperature for silicone polymers is minus 120 degrees C. And another way to think of this at the molecular level, that at this temperature, a coordinated motion of 50 repeat units or more can exist in the main chain to allow these polymer chains to start to snake past one another for flow or in a viscous sense. So, okay, so with all that, we've said that silicones are very stable to high temperature and oxidation in chemical and biological environments owing to long, strong bonds in the main chain. Polysiloxane fluids and resins can be obtained by a reaction known as hydrolysis. And so this can be had by starting with a dichlorosilane. So here at left, we have dichlorodimethylsilane. And if it reacts stoichiometrically with one equivalent of water, we can see that water reacts to eliminate HCl and leaves behind an OH group that can be found and shown here. So with a 1-to-1 reaction, a chlorine leaves with 1/3 of the water molecule, and we now bond in an hydroxyl residue to make chlorohydroxysilane from that dichlorodimethylsilane. Should this same reaction happen twice on the same molecule, so 2 equivalents of water to the dichlorodimethylsilane, we would end up with the dihydroxysilane shown at right. The SiOH group shown here is called a silanol. And silanols are self-reactive and form, so if we have two silanols, we can form a silyl ether, which is the silicon equivalent of a carbon-oxygen-carbon ether. So that is to say that these silanols shown here can react further to eliminate water this time. So if we were to eliminate that component there, we would allow this oxygen to bond to that silicon to make our silicon-oxygen bond to the next repeat unit, with the former already having been installed from before. And so this explains how siloxane fluids and resins can be formed. We've seen that chlorosilanes are hydrolyzed with water, and they can give a mixture of chlorohydroxy and dihydroxysilanes with the functional group there that's generated called a silanol. Okay, so polydimethylsiloxane elastomers can be heat cured in many cases, and so many of these polymers before cure are made up of long chains with many repeat units. So as we were mentioning before with the SiO R repeating pattern here of N, the value of N can be 2,500 to 11,000. Many of these repeat units tethered together to make a long polymer chain. Hydroxylation is a reaction that is important for this lab that finds a way to react SiH units with vinyl groups on two different polymer chains. So in the cure reaction of our silicones, we will see two different silicone polymers mixed together, and a catalyst will be added to drive this hydroxylation reaction. So shown here in the figure, showing the chemical transformation, we see one polymer chain bearing the vinyl groups at left. And so that vinyl group represented with showing the CH2 double bonded CH unit is shown here. And there are two highlighted for us. And these could be two different polymer chains shown as the squiggle. All right, and then the other complement material needed is the hydroxylane polymer, and we see that listed here with the SiH bonds occurring in several highlighted spots. This reaction works with a catalyst, typically a transition metal, and adds the SiH functionality across the carbon-carbon double bond. So we can expect to find this hydrogen appended to the further carbon site typically, and a new bond forming between the silicon and that nearest carbon. So to highlight where the hydrogen formerly as a hydroxylane is now found, we will show that right here. So one of those hydrogens is from the hydroxylane functionality prior to cross-linking. Okay, and we see the same thing above. So this might be a moment where you pause the video and try to identify in the cross-link between the two polymer units where that hydrogen is transferred from the hydroxylane, which hydrogen in the bridge is due to the hydroxylane having added across the vinyl group. Yes, so hopefully again you identified that hydrogen there, one of those two CH2 hydrogens for that feature. Okay, so this slide has this kind of laid out for us a little more clearly, so we'll just allow the animation to show that for us. And move on. So we take advantage of this reaction to allow for a pouring of pre-cured mixture of those two different silicones, or polyvinylsiloxane with polyhydroxylasiloxane mixed with catalyst, pouring over top of a mold. So in this fabrication schematic, we see a mold having topography defined by either SiO2 or silicon nitride or metals or even photoresist, providing kind of a pattern, laying on top of a flat piece of atomically flat silicon chips like we would normally find in our microelectronics. By flowing the PDMS over top of the material, it will occupy all the wells and mold as a liquid over top of the topography of that mold. And then by curing, typically by advancing the temperature of the material upwards of 80 degrees, in the presence of the catalyst already mixed in, that cross-linking reaction will occur. And so we can represent that with, bonding of the chains across to one another. And that sets the PDMS into a solid object that will no longer flow under its weight and retain the shape that was inherited by molding. So upon releasing of that after cure, we inherit the PDMS structure that has the anti-surface properties, or the opposite topography of the mold. And this is the sort of set PDMS-based silicone that can be used for soft lithography. Soft lithography is a technique where we apply a cured mold like we have here and wet it with molecular ink on the surface and apply this to surfaces for transfer of those molecules. Typically, thiols can be added to the surface, and those thiols would stick to a surface that is compatible with the thiol. A thiol is any organic residue, generalized here as just R, terminated with an SH unit. So the thiol group is the sulfur equivalent of a hydroxyl group or an OH group or an alcohol group. So in this approach, our PDMS acts as a stamp for pattern transfer. And because it's elastomeric, it can conform to a lot of different topographies and 3D objects. It's inert, so it won't react with any ink that is applied thereafter. So that stamping technique will be successful. And it's hydrophobic, so we can absorb ink from water or other kind of media and take advantage of that. PDMS, however, does swell in organic solvents, and so one needs to be cautious of that if we want to maintain the sort of pattern as far as the length of the features and the height of them, as well as the pitch or the depth shown there in our image. PDMS is also known to be gas permeable, and so this can be advantageous when working with devices intended for biological environments, as essential gases can permit through that PDMS owing to its low glass transition temperature. So here's the photolithography step where you see the ink, typically a thiol like we show in this inset here, where a sulfur end with another functional group X, which could be simply hydrogen terminated or other features there, can be applied to a gold layer resting on top of a substrate of silicon. So this inking of the PDMS and transfer of those molecular species to the surface transfers a self-assembled monolayer where these molecules, if in the form of a linear alkane chain, pack into a tilted array of those molecules called a self-assembled monolayer. This molecular ink can be used for further patterning, such as the deposition of particles or materials that have an affinity for X, or we can do etching to transfer the pattern of those molecules deeper into the substrate, that is the silicon. This is how a lot of very elegant and kind of state-of-the-art nanofabrication techniques have been explored for generating all sorts of functional surfaces and devices. Other PDMS uses include microfluidic devices, where you can see now how a master mold could be used to transfer a channel into a PDMS that has been poured and cured over top of that. So our little green bar here provides a trench in the cured PDMS that's released from that replica, or from that mold as a replica. Drilling can then be done to apply tunnels from the top through to that trench that's inset into that PDMS. And after priming surface for bonding, that by plasma treatment, that can be applied to a solid structure to act as the base. By doing this approach, we would now have a microfluidic channel that can allow microliter amounts of water to pass in through one port and out through the other, and we could study reactions or other kind of microenvironments in that channel. So lots of different applications in industry for a microfluidic device, and so I invite you to access some of that information at the following link. Here's a photograph of a microfluidic channel with elaborate design on over top of glass, so we can photograph it with a microscope. And here again is another view of a functioning microfluidic channel where microvalves have been included to allow the passage of the fluid from the inlet to the outlet via a valve approach. Okay, so with that,